Alternating current is a fundamental in electrical and electronic engineering because it lowers used to power distribution, communication system, and electronic devices. In the current circuits, AC circuits contain voltage and current that are continuously defined. The behavior of AC circuits depends not only on resistance but also on inductance and capacitance, which introduces the excitancy differences between voltage and current. To simplify these circuit calculations, engineers use concepts such as impedance, which includes the effect of resistor, capacitor, and inductor. Mathematical tools like phasor and complex numbers are applied to represent magnitude and phase relationships effectively. This network analysis is essential in efficient power system communication circuits and electronic devices, ensuring reliable and stable electrical performance. Next is
And for our objectives, the first one is to determine the effects of resistance, inductance, and capacitance on circuit performance. Number two, to calculate impedance, current, voltage, and power factor in RLC circuits. And lastly is to compare theoretical calculations of series and parallel circuit simulation.
In the procedure, the laboratory experiment was conducted using NI multisim to simulate various AC circuit configurations, including pure resistance, inductance, capacitance, as well as the series and parallel combination of RL, RC, LC, and RLC circuits. For each circuit, the voltage, current, impedance, and power were measured using virtual instruments. Theoretically, calculations were then performed to determine the impedance, reactance, current, voltage, power factor, and power values. Finally, theoretical results were compared with the simulation data to analyze the electrical behavior and performance of each AC circuit configuration. Here are the sum of examples in series. The series circuit was constructed in multisim by connecting all resistors end-to-end with the DC voltage source. The correct resistance values were assigned to each resistor. After completing the wiring, the simulation was run. A digital multimeter was used to measure the voltage across each resistor and current flowing through the circuit. The measured values were then compared with the theoretical calculation to verify that the same current flows through all series components. And next is the parallel. The parallel circuit was assembled in multisim by connecting all resistors across the same voltage source. The resistance values were set according to the circuit diagram. After running the simulation, the voltage across each branch and the current through each resistor were measured using the digital multimeter. The results were com- compared with the theoretical calculation to confirm that each branch has the same voltage while the current divides among the parallel paths.
And for the results, the laboratory showed that the theoretical calculations and multi simulation results closely match, confirming the accuracy of AC circuit analysis. Resistive circuits consume real power, while inductive and capacitive circuits mainly stored and released energy. RLRC, LC, and RLC circuits behave as expected, and parallel circuits verified that voltage remains the same across the branches, while current depends on impedance. Overall, the experiment successfully validated the fundamental principle of AC circuits, with only minor differences due to routing and simulation limitations.
For our data analysis and discussion, this experiment successfully verified AC circuit principles by demonstrating near-perfect agreement between theoretical calculation and multisim simulation across pure RLC, series and parallel, RLRC, LC, and RLC configuration. Purely resistive circuits maintained an in-phase unity power factor, while ideal reactive elements dissipated zero real power with negligible nanowatt level simulation rounding errors. Series and parallel combinations strictly followed expected Pacers relationship, with inductive circuits causing a lagging power factor and capacitive circuit a leading one, despite the software limitation preventing the multisim wattmeter from directly measuring reactive power VAR. The precise alignment of simulated voltage, current, impedance, real power, and power factor fully validated the theoretical calculations. Next slide, please. To summarize, we achieve our objectives by analyzing pure and RLC circuits under AC excitation. When we compared our theoretical with multisim simulation, the results lined up almost perfectly, which validates our circuit analysis. Any tiny differences were just due to rounding and simulation precision. One thing to note, we couldn't directly compare reactive power because multisim wattmeter only measure real power. However, the ideal inductive and capacitive circuits gave us near zero real power readings, providing that they just exchange reactive energy with the source rather than dissipating it.